Hey, welcome to another exciting chemistry class with stoichiometry. We're doing mass. This is practice sheet number 2, problem number 3. So again, we have all of our steps that we have right here that we're gonna need to go through in order to figure out our stoichiometry problem. So if we read the problem and we start, during a combustion reaction, butane burns in the presence of oxygen. It produces carbon dioxide and water. What we need to do is determine the mass of carbon dioxide produced when 0.85 grams of butane, which has the formula of C4H10, reacts with an abundance of oxygen, which again, abundance of oxygen just means it has as much as it's going to possibly have. So the first thing we need to do is figure out what is the skeleton equation. So let's go back and read again. During a combustion reaction, butane burns in the presence of oxygen. So we have to come up with our skeleton reaction. So here we're going to start out with butane, and we're going to copy that, and we can paste that right down here. Okay, so we got that pasted. And then that's going to be in the presence of oxygen. But again, as always, we have to go, is oxygen diatomic? Is it one of our 7 diatomic elements? So we can look at our periodic table, which again, here's our periodic table. If I scroll up from our packet all the way back up to the top, and we get down to that packet and we say oxygen is right here. Now remember that diatomic elements, and I'm just going to scroll down a little bit, make a 7 in the periodic table right here. So there's nitrogen, oxygen, fluorine, chlorine, bromine, iodine, plus our hydrogen over here. So 6 elements make the number 7, and yes, oxygen is diatomic. So let's go ahead and go back to it. So that means, since it's diatomic, that means we have to have a subscript of 2. So we're going to go ahead and put our 2 right there. And then it says it produces carbon dioxide. Now, if you don't know what carbon dioxide is, carbon and 2 oxygens. So it's just going to be CO2 and water, okay, which we get H2O. So there's our skeleton equation. We're pretty good about that. Now we have to go ahead and balance it. So we're going to balance our skeleton equation. And I'm going to say that the best bet to do that is put down the elements on each side. So we're going to put down carbon, hydrogen, and oxygen. So that's what we have on each side. Now I can go over here. Oops, I don't want to do that. I can do that on this side too. Carbon, hydrogen, and oxygen. And we're going to go ahead and with this, we're going to add our how many we have of each one. So we got to put down the number. I have 4, okay, so we're going to put a 4 there. Of hydrogen, we have 10, it looks like. And of oxygen, we have 2. And on this side of carbon, we have 1. Of hydrogen, we have these 2 over here. And oxygen, we have it in 2 spots. We have 2 here and 1 over here, so we have 3. So we're going to save the oxygen by itself. Now, the reason I like to save oxygen by itself is because I have oxygen alone over on the other side. Even though it's diatomic, all that means is I have to have an even on this side over here. So I have to have even oxygen on this side. So I'm going to go ahead and I can do the carbon first, or I can do the hydrogen first. Let's start by doing the hydrogen. I have 10 hydrogen over here, and I have 2 on this side. So I can only change the coefficients. As you remember, we can't change the subscripts. What times 2 equals 10? Well, the answer is 5. So once we do that, we know that we have 10 now on this side, and I can strike through that or just get rid of that one right there. Okay, so I'm just going to highlight that with black. Okay, so now I have 10. Okay, but I also changed my oxygen. So I have 5 times 5, so I have 5, 6, 7, so that changes that to a 7. Now I do know where we're going here. Okay, I can't change this to 7 because it can only be even. So that means I have to make this an even number. So one of the things that we can do with this is just go ahead and double that number. Let's go ahead and double that number and see where we're at. That means that our hydrogen now is at 20. Okay, and I can get rid of this. Okay, but I got to come over here and get it. So I'm going to put a 2 right here. So 2 times 10 is 20. And I can get rid of this one. Okay, so now I have that, but I've changed my carbon on this side. So let's go ahead and change my carbon. I have 8 now on this side. And now I need to get 8 on this side. So I have this. I also, let me change my oxygen. I have 10, 11, 12 on this side. So let's get rid of that, or change that to 12. And so I know that I can get rid of those. Okay, so I got rid of those. So I have 12 here of oxygen, 10, 11, 12. Carbon, I have 8. Okay, I still only have 2, and I have 20 there, so we're good there. But now I have to get 8 over here, so the only way we can do that is by putting an 8 right there. Now I can change this to an 8. We'll get rid of this. But now my oxygen has changed. So my oxygen is now 16, right? 16 plus the 10 over here is 26. Now the nicest thing is I have an even number. So we can do the even number. So now I have 26. Now I need it on this side. So what times 2 equals 26? Okay. It's going to be 13. Okay. So 13 times 2 equals 26. So that means that this changed to 26, and we can get rid of this. Now let's go ahead and double check and make sure we have carbon. I have 4 times 2 is 8. I have 10 times 2 is 20 for my hydrogen. I have 13 times 2 is 26 for my oxygen. On this side, I have 8 times 1 is 8 for my carbon. I have 8 times, well, let's do the hydrogen first. I have 10 times 2, which is 20 for my hydrogen. And then my oxygen, I have 8 times 2 is 16, plus 10 times 1 is 10, so 26. So there is my thing. So my molar ratio is going to be 2 to 13 to 8 to 10. Now, one thing I want to do is I got to look at it, and we're going to make it bold, and we're going to change its color here so we know where it's at. So there's the molar ratio. My problem is, can I reduce it, though? It's not a problem, but can I reduce it? Those are big numbers. They will work, but can I reduce it? Well, because I have this 13 right here, I can't reduce it. I don't have a number that's in all of them are in common. If it was an even number, we could cut it in half, but we can't do that. So there's our balanced chemical equation. So now we have a balanced chemical equation. Now we have to go ahead and start our stoichiometry. So our stoichiometry is going to start with the number that's in the problem, which is going to be right here, 0.085 grams of butane. So we're going to go ahead and I'm going to scroll down just a little bit, and I'm going to put in 0.85 grams of butane. And I'm just going to go ahead and copy that real quick. And we'll paste it. Okay, now the next thing we're going to do is, as always, we're going to put our times in a line. And we have to put grams of this in the bottom. So I'm going to just pop there and just kind of get that over there. And we're going to put grams of this here. Now I'm going to get rid of that. Now the only way I have grams, if you remember, we have things that are equal. If I go back up to the top, I don't have it up here, but if I go into the packet, we'll show you the packet, and I scroll down, we know that if we get down here to the bottom right here, we see 1 mole equals Avogadro's number, which equals the molar mass in grams. So if I want to change it to moles, which I have to, we have to use the molar mass in grams. So let's go back here, the molar mass in grams. So we have to calculate out the molar mass in grams, but up here we have to convert it to 1 mole, okay, of butane. So we'll put that 1 mole of butane in there. And then we're going to set it up for our next step, because remember there's 3 steps here, and we will underline this part right here. Okay, so let's calculate out our molar mass of butane. So if I go ahead and I paste the formula for butane, I know that I have carbon, and we have 4 of them. Okay, I have hydrogen, and we have 10 of them. Okay, so 4 times the weight of the atomic weight of carbon, which is 12. Okay, so we're going to put the times in there, and that's going to equal, okay, should equal 48. We'll double check that. And 10 times the atomic weight of hydrogen, which is 1. And that would equal 10. So let's go ahead and double check this. First, let's double check and make sure that the atomic weights are right. 12 for carbon and 1 for hydrogen. So let's go back to our packet here and scroll up to get our periodic table. Okay, hydrogen is 1. Okay, that's the atomic weight, and the atomic weight for carbon is 12. So we're good with that one. So let's pull out get our calculator out, and let's put it in. So let's double check. 4 times 12 equals 48. And we're going to add to that our 10, and so we should have 58. So our molar mass equals 58 grams, okay, of butane. So now we're going to take this 58 grams and place it right here in our stoichiometry equation. And then we can go ahead and, again, I like to cross out anything that we can cross out before. So let's go ahead and cross out what we can. So we can cross out our grams of butane, because I have it on top and I have it on bottom. So let's go ahead and get rid of that. So we're just going to highlight that to get rid of it. Okay, so let's highlight that. So we get rid of that. So right now we have it in moles, okay, of butane. But I have to go from moles of butane for what is the question? Determine the mass of carbon dioxide. So I got to figure out my mass of carbon dioxide. So I'm going from 2 moles of butane to 8 moles of carbon dioxide. Now, if we go back up to our steps, okay, we're going to use the molar ratio here, which is 2 moles of butane and 8 moles of carbon dioxide. So since I have moles of butane up here, I have to, on the bottom, I have to place our 2 moles that I have right here of butane. So we're going to put 2 moles of butane on the bottom. And then we're going to put this right here on the top. And that's going to be 8 moles and what that's going to equal, well, it's not going to equal yet because we still have to go in with the rest of it. So we're going to go ahead and highlight this part. All right, highlight but underline it. And now I can get rid of my moles of butane and moles of butane. So I'm going to get rid of those. And again, we'll just get rid of them that way. So now they're gone. So now I have moles of carbon dioxide, but I want the mass of carbon dioxide. So now I got to convert these moles here back into, by multiplication sign and a line, okay? And so on the bottom, we're going to put 1 mole of CO2. And let me just undo that. Okay, so we have 1 mole of CO2, and how many grams is it? So we're doing the molar mass here. So 1 mole equals how many grams? Okay, so what we're going to do on this one right here is we have to figure out the molar mass of carbon dioxide. So let's go down here, and we're going to put down that we have CO. Don't want that. We're going to have CO. There's our formula. So we have carbon and we have oxygen. Well, we have 1 carbon. We're going to times that by 12. That's going to equal 12. We have 2 oxygens times the atomic weight of oxygen, which is 16. That's going to equal 32. We add those together, and we're going to end up with 44. So our molar mass is going to equal 44 grams for CO2. Okay, so this is going to go on top. So we're going to put that, we're going to copy that, and we're going to place it right here. Okay, so now we have our conversion factor there. We'll underline that. And now I look at I have moles of CO2 here, moles of CO2 there, so I can get rid of those. So we're going to go ahead and get rid of those also. So now I'm left with grams of CO2. Now, is that what we're looking for? Grams of CO2. So let's just see if that's, didn't want to do that. Is that what we're looking for? And if I scroll back up to the question, it says determine the mass of carbon dioxide. Well, grams is mass of carbon dioxide, so we have to figure that out. So I have it left in grams of carbon dioxide, so all I have to do is the math. So let's go ahead and pull up our calculator again. We'll clear it, and we're going to do the math. Remember, we multiply by the top, divide by the bottom, multiply by the top, divide by the bottom, multiply by the top, divide by the bottom. But wherever there's a 1, we don't have to do that because 1 doesn't change our value. So let's go ahead and start off with 0.85 divided by 58 times 8 divided by 2 times 44. Hit equals, we end up with 2.579. So let's go ahead and put that in there. 2.579. I don't think we have to put any more because I believe that we have to go back to how many significant figures. We need to have only 2 significant figures. This 0 is not significant, okay, because it's preceding. Okay, so we need to go to 2. So I got 1, 2. I'm going to put a line right there. 7 says we round up. So we're going to get rid of that, go back, change that from 5 to a 6, and we have our answer. We highlight it, change that color right there to nice green so we can see it. And now we have our answer, and there's our stoichiometry problem. That's the answer to it. Grams of carbon dioxide. We're looking for grams of carbon dioxide. So that's the question number 3 from practice sheet number 2. Hopefully this helped you out. And as always, hey, go Mohawks. Nelson out.